Hello everyone, today we're going to explore how you can use EMPIRE-XPU to simulate the antennas found in mobile devices. Our specific focus in this tutorial will be on simulating a 28 GHz patch array with the ultimate goal of understanding the incident and absorbed power density. Along the way, we'll also have a look at other important antenna parameters such as S parameters, the antenna far field, and electromagnetic field animations. First, we need a mobile device and an antenna. To save time, we will use a template that already exists in EMPIRE. Go to the Templates page and select the mobile phone template. Next, select the simulation of dielectrics and metals as narrowband lossy. In this case, we will select the 5G patch antenna as the simulated antenna. After clicking OK, the 3D Design tab opens and displays the smartphone model. The next step is to give the project a name. To do this, click File, Save As, and enter a name. To save time during the simulation, by default the simulation domain for this template only includes the area around the patch antenna. To expand the simulation domain to include the entire device, click Simulation Setup and deactivate the option User-Defined Simulation box. Click Create Mesh, and then Redraw to make the changes visible. Switch to the 2D Design tab, and locate the Field Monitor submenu on the left side of the screen. To remove Field Monitor 2 from view, simply click the lamp icon next to it. Then, click the Create Field Monitor button in the top bar. Choose the option for a full field volume, and confirm by clicking OK. In the XZ side view, the field monitor's height is visible. You can adjust this height either by using the slider or by entering a specific value. If set to 6000, the power density will be evaluated at a height of 2 mm above the screen. Right-click on Field Monitor 3, select Edit and open the Plot Options tab. Change the field to Spatial Average Power Density and the direction to outflow. Change the normalization type to power and add ports 3, 4, 5, and 6. To consider all active ports of the millimeter wave antenna for total power normalization to 1 watt. Set the maximum scaling value to 4200 and the range to 40 decibels. Switch to the Simulation tab and run a full simulation. Wait for the simulation to finish. At the start of the simulation, the simulator optimizes the solution strategy to match the specific problem in hardware, guaranteeing full parallelization and optimal utilization of all cores. The simulation ends when the energy decay is greater than 40 decibels and the field convergence error is less than 1%. Open the 2D Results tab. The S parameters of this array show a resonance around 28 GHz for all 4 patches. Switch to the 3D Results tab. Field Monitor 3 displays the incident power density. To obtain the maximum value, right-click on the plane of the monitor and click Add Marker. The maximum power density is approximately 4 kilowatts per square meter. To make the far field monitor visible, click on the lamp icon next to it. The far field shows that the antenna is emitting mostly upwards, but the shape of the emission is distorted by the metal frame of the phone. Hide Field Monitor 3 and show Field Monitor 2. Field Monitor 2 shows the phase loop of the electric field. Show only the XY plane of the monitor and start the animation. Emission occurs at the top and bottom of the patches. To see the electric field of other planes, activate the corresponding monitor. The side view shows the emergence of the wave above the antennas, and it is also possible to see how the near field merges into the far field pattern. The power density also strongly depends on the height of the monitor. You can change the height of the monitor, and the result will be updated immediately. After you are done, change the height back to 6000 and go back to 2D design. Next, we want to evaluate the absorbed power density. For that, we need to model a material which has the properties of human tissue. Open the top view and add a new group called Skin. Expand the group and adjust the height range, setting the minimum to 6000 and the maximum to 8000. Then, double-click on the conductor property, choose the Gabriel Material option, and select Tissue Skin. The Gabriel Material property calculates the material parameters specifically tailored to the simulation's target frequency. In this tutorial, we're utilizing a flat phantom represented by a rectangular box placed above the screen of the mobile phone. Click on the button Create Box and enter the dimensions as shown in the video. Optionally, you can add additional tissue layers on top of the initial layer. However, at this frequency, the majority of the power will be absorbed near the surface. Consequently, additional layers are unlikely to significantly impact the results. After clicking OK, you can see the contours of the box. Change to the XZ side view and get the skin box into view. The red and blue lines on the right and bottom of the screen show the boundary lines of the simulation cells as drawn in the automesher. The boundary of the skin box does not match these lines because an advanced material is being used. To fix this, we will utilize a mesh hint. Right-click on the skin property and choose Add Property. Select Mesh Hint and enter Zmin and Zmax in the text field under Edge Use. Click OK to confirm the settings and press the Create Mesh button in the top bar. The lines of the box and the mesh will now be at the same height. Go to the Simulation tab and click Simulation on the left, if it is not already selected. Start Complete Simulation and wait for it to finish. Switch to the 2D Results tab. The scattering parameters are different than before because the skin box has detuned the antenna. Open the 3D results and hide the skin group. Next, show and expand Field Monitor 3. Right-click on the existing marker and click Move to Maximum. The absorbed power density is approximately 0.37 kilowatts per square meter, which is 10 times less than the incident power density. As a final step, we will look at the near field of the antennas. Change the transparency of the skin box and activate Field Monitor 2 instead of 3. Initially, focus on the XY plane. While the pattern bears resemblance to the configuration before integrating the flat phantom, a notable difference emerges. The electric field is substantially stronger. To understand the reason for this phenomenon, switch to a side view and activate the relevant plane. it is clearly visible that a significant portion of the wave is reflected at the skin surface. This also explains why the absorbed power density is lower than the incident power density. Thank you for watching the video. If you have any questions or suggestions, please leave them in the comments below.